Okay, as promised, I'm going to solve this problem from class. So I wrote a couple of things here that just to get us going. So first of all, I gave you temperature in Celsius, and I gave you the reaction or the rate constant at all these different temperatures. And I wanted to so we're using this equation. This equation is called the Arrhenius equation to answer question A, which is asking us to find the activation energy, which is EA. And we're not actually solving for EA with this equation. We're using this equation, we're going to graph, because it's a y-intercept form of an equation, the natural log of K versus 1 over T. So to get the activation energy, we're going to need to graph the natural log of K on the y-axis, see the y here, versus 1 over T on the x-axis, right there. And when we get that graph, we're going to take the slope of that graph. In your calculator, you can actually do a linear regression. I am not sure how to do that, but you can. And honestly, you don't even really need to graph this to be able to answer this question, but you probably should, just to make sure it's a straight line. And then you're going to get the slope. And the slope, so to solve this problem, just so you know where we're headed with this. So ignore B and C for a second, and we're going to kind of move down. So up here it tells us that the slope, M, so M equals slope, is going to be equal to the negative of our activation energy over the universal gas constant. So once we graph this and we get the slope from the graph, we can plug that in here, make that equal to negative activation energy over R, and if you remember, R is the universal gas constant, and it's equal to 8.314 joules per mole Kelvin. So we can just plug that in there, we'll get the slope from the graph, and we can solve for EA. So that's where we're headed for part A. That's what we're going to do. So you're going to get your calculator, and you're going to, now remember, temperature in this, so we have to get 1 over T. Temperature's got to be in kelvins, and here I gave them to you in degrees Celsius. So I just went ahead and converted all of our temperatures to Kelvin. So we're going to use this, and we're going to take 1 over that to get this, because we need to graph the natural log of K versus 1 over T. So I went ahead and converted temperature to Kelvin, and then took that and made it 1 over the temperature, and I got all of these numbers. And you're going to put those in your calculator under list 1. And then for this, you need the natural log of K, because that's what's going to be on the y-axis. And so I made a second list 2, that's going to be the natural log of K. So there's all your K values, and there's the natural log of K values that you should get. So you're going to make a graph in your calculator, and that graph is going to be a graph of natural log of K on the y-axis versus 1 over T on the x-axis. And you should get something that looks like, well, I actually didn't graph it, I'm sorry, but I'll show you what it should. It should be a graph that looks something like this. So starting somewhere between -5 and -6, right, you should have a line kind of sloping downward like this. And then this would be -11-ish. Okay, so you're going to get a downward sloping graph. And hopefully you realize you're going to get a downward sloping graph because your slope is going to be negative, which means that you're going to get a downward sloping graph. Excellent. Now, to get your slope, you can do a linear regression in your calculator, or you can do my old school method, which slope is delta y, the change in y over the change in x. That just means that we're going to use these numbers up here, right? The change in y is going to be this. So any of these two numbers will work, but I always like to use the two furthest apart numbers, and I don't know why. So I'm going to take this number, and I'm going to subtract this number. Okay, so to get my slope, I'm going to take, so slope is going to be equal to the change in y over the change in x And so we're going to take negative 5.757 and subtract negative 10.589 on the top. And then the change in x is going to be this minus this, because that's what's on your x-axis. So 1.907 times 10 to the negative 3 minus 2.160 times 10 to the negative 3, like so. Okay, so that's going to equal your slope. So just work this out, and you're going to get a number that you're going to get negative 1.9 times 10 to the 4th. So that's your slope. So we're going to plug that in here, because remember, slope is going to be equal to the negative of your activation energy divided by that gas constant. So we know that negative 1.9 times 10 to the 4th is going to be equal to the negative of your activation energy, which is what we're trying to find, over 8.314 joules per mole Kelvin. So solving for EA, you're going to have negative 1.9 times 10 to the 4th. You're going to multiply that by negative, because I carried that negative sign with this, so I can get rid of the negative, because your activation energy can't be negative. It has to be a positive number. So just remember that it can't be negative. And when you solve for activation energy, you're going to get a pretty big number. I got 1.6 times 10 to the 5th joules per mole. And just so you know, activation energy is mostly reported in kilojoules, not joules. So, you know, if you multiply by 1,000 joules per kilojoule, you can put it into kilojoules per mole instead of joules per mole. So either of these answers is fine, but if they ever ask for it in kilojoules, you might want to put it in kilojoules, or you might just want to put it in kilojoules, since activation energy is mostly reported as kilojoules. So that answer is part A. So this was A. Okay, B asks for the value of the rate constant at 430 degrees Kelvin. So part B, we know that we have a new temperature of 430 degrees Kelvin, and we want to know, what the activation energy, or sorry, what is it asking for? Sorry, the rate constant. Activation energy is not going to change, so it's going to be the same. That doesn't change with temperature. So we're going to use that form of the equation that I gave you, where, actually I don't even think we need to do that. No, we do. So this form of the equation that I gave you, where you take the natural log of K1 over K2. So we've got two different activation energies, is equal to the activation divided by that gas constant times the, I guess, difference between 1 over T2 minus 1 over T1. So, oh my gosh, I've been talking this whole time and I didn't move my paper up. I'm so sorry. So there it is. There's the equation that you're going to use. So this equation you're going to use because you were given a new temperature, and you're asked to find the rate constant at that new temperature. And notice that the temperature they ask about, which was 430 Kelvin, is not on this. So you can't just look it up on the table. You're going to have to plug some numbers into the equation. So to determine the new rate constant, so we have rate constants for all of these temperatures, but we don't for this. So to do that, to determine it, you're going to use this equation. And notice that we have two rate constants and two temperatures. And your activation energy you've just calculated, so you already have your activation energy. I would use the one in joules because your gas constant, remember, is in joules. And you can pick pretty much any of the rate constants and temperatures that you had up here in this little table for the other K and the other T. So I'm just going to go ahead and use the first one right here, so this and this, and we'll call those T2 and K2. So we're going to get the natural log of K1, which is what we're trying to find because we don't know that rate constant, and K2, I'm just going to use that 2.52 times 10 to the negative 5 per second that I got right off this data table. Sorry if I'm making you dizzy. And then T2 is going to be 462.9. So we'll go back here. Okay, EA, we know, because we just calculated it. And remember, we're going to use the one in joules per mole because we're dividing by the universal gas constant, which is in joules per mole Kelvin. So we want those to be the same. And then we're going to take 1 over T2, and T2 we decided was that first trial, 462.9, and that's Kelvin. And we're going to subtract the new temperature that they gave us in the question, which was 430.0 Kelvin. So we're basically going to solve for this. This is what they're asking us for, is, you know, from what is the value of the rate constant at that temperature. So I guess the tricky part about this is you want to always make the one you're solving for the one on top. I guess it doesn't really matter, you'll ultimately get the same answer, but it just makes it easier, I think, to solve the problem. So, okay, let me move my paper down and add a new sheet of paper just so that I have room to write all of this. So, take the natural log of this, or actually, let's do the inverse natural log of everything. So K1 over 2.52 times 10 to the negative 5 seconds, or per second, or over a second, equals E raised to the power of negative 3.18. So if I solve for all of this, I get negative 3.18. To get rid of that natural log, we're going to do the inverse log of both sides, which means you're going to get rid of the log on this side and raise this, or E, to all of this, which is this number. And if you solve for K1, you get 1.0 times 10 to the negative 6, and then it's per second. Okay, so that's how you get the new K value given another K value and its temperature, and then the new temperature for the K value you're trying to solve for. So you're using this fun equation, which is a derivation of the Arrhenius equation. All right, let's see. Part C says, using the data above, so part C, using the data above, calculate the rate constant for the rearrangement of methyl isonitrile. By the way, that's a typo. It should say methyl isonitrile at 280 degrees Celsius. So again, you're basically doing exactly the same thing that you did here, but this time you're solving for a new rate constant at, instead of 430 degrees Celsius, you're solving for it at 200 and what did they say?